With this video, class 12, we are going to start magnetic effects of current. Okay, where of course we are going to discuss magnetism being a result or consequence of electric current flowing. Okay, so whenever electric current flows through a conductor or a wire, what it produces is magnetism. Alright, so that is what we are going to discuss in this topic. Now, this topic is also called magnetostatics. Okay, this topic is also called magnetostatics because in this topic we are going to discuss we are only going to discuss constant current flowing through a wire, remember. We are not going to discuss cases of variable current flowing through a certain wire or through a certain conductor. Now, when a constant current flows through a conductor or a wire, what happens is at a given point, this particular current, constant current flowing through this wire produces a constant magnetic field or the same magnetic field. Now, this is the reason why it is called magnetostatics, because it is going to produce, this constant current is going to produce the same or constant magnetic field. That is why it is also called magnetostatics, remember. Okay, so in this topic, remember, in magnetic effects of current or magnetostatics, we are only going to discuss about cases where constant current is flowing through a conductor, remember. Okay, now to start this topic, okay, first of all, we are going to discuss about something called Oersted's experiment, which you've studied about in class 10 also. All right, so this is about this experiment was done in the early 19th century. Okay, I mean the first half of the 19th century, maybe in the 1820s. Okay, so what happens is you have a cell, all right, and a current is flowing through the cell. This is the key. What was noticed by Oersted is that whenever he had a of course a magnetic compass close to this current carrying conductor. So what was seen there is that whenever this key was closed and current was allowed to flow through this conductor, okay, what was seen that whenever current is flowing through this conductor, this magnetic needle got deflected. All right, and it was also seen that when the direction of the current was changed, the direction of deflection of the magnetic needle also changed. Okay, you've heard about this in class 10 also. Now, the direction of deflection of the magnetic needle is given by Amperes swimming rule. Okay, so what is this Amperes swimming rule? So imagine yourself swimming along the wire in the direction of the current. Okay, so what is happening is we have to imagine yourself, so since current is flowing in this direction, so it's like we are swimming along the length of the wire. Okay, we are swimming along the length of the wire in the direction of the current. Okay, furthermore, facing the compass. Okay, so I have drawn a picture over here, all right, where you are swimming. All right, and say for example you are facing the compass over here. The compass is down below here. My picture is not very perfect. You are facing the compass and you're swimming along the length of the wire in the direction of the current. So what Ampere's swimming rule tells us is the deflection of the needle will be in the direction of your left hand, or the magnetic needle will deflect towards your left hand. So whichever side is your left hand, so in this case the other side, this side is your left hand, so the magnetic needle is going to deflect in that direction. Okay, while you're swimming, in this case you're swimming towards this side, so in this case your left hand will be here on this side, so therefore the magnetic needle is going to deflect this way. Okay, so that is what Ampere's swimming rule tells us. So going very briefly through this point, because you've done this Oersted's experiment, okay, and the direction of deflection of the magnetic needle in class 10 also. All right, so let me jump to the main topic, all right, which is very, very important from your examination point of view also. Okay, so it's like the real magnetostatics for you starts with this law, which is called Biot and Savart's law. Okay, two different persons. So Biot and Savart's law. Let me tell you what it gives you first. Okay, say for example we have a current carrying wire, all right, the current flowing being I. So say for example this particular wire has a certain length, say for example L. Now this complete length is made up of small lengths joined together, okay, makes up this complete wire. So say for example the small length that we are considering is this, which is dl. So as you can see, from here to here is our dl. So these kind of small dls makes up the complete wire. So this dl is called an elemental length. Okay, so dl is the elemental length. Dl is the elemental length, mind you, and I into dl. The current is flowing through dl and of course through the whole wire is I. So I into the elemental length, this has a name. This is called current element. Okay, of course dl and also idl can be considered to be a vector whose direction is the same as the direction of flow of current. So if I ask you what is the direction of dl, the direction of dl is this, because in here current is flowing this way. Okay, so what is observed is, of course, whenever we have a current flowing through a wire or through this elemental length, okay, what is observed and what has been proven today, of course it's proven, okay, is that this current carrying wire produces a magnetic field at all points surrounding this wire. A magnetic field is created, okay, is developed. All right, so and of course, you know, theoretically the magnetic field generated by a current carrying wire, okay, a current carrying elemental length also, okay, extends up to infinity, of course. Okay, like theoretically I have a magnet, say for example my pen is the magnet, okay, theoretically the magnetic field generated by this magnet, or the magnetic field that we have around this magnet, will extend up to infinity theoretically, but of course practically in reality that doesn't happen. Okay, so this current is flowing through this wire and also through this elemental length. So this current element IDL, okay, will also generate its magnetic field, and we want to calculate the magnetic field at point P. Okay, so what does Biot and Savart's law give you? It gives you the expression for the magnetic field intensity at a certain point due to a current element, remember. So what does it give you? It gives us the expression for the magnetic field intensity at a certain point due to a current carrying elemental length dl. Okay, so it's something like your Gauss's theorem. Okay, it's something like a Gauss's theorem in electrostatics. All right. So let us look at the law. The magnetic field intensity, so dB, remember capital B will denote your magnetic field intensity, like capital E denoted your electric field intensity. It denotes magnetic. Mg is magnetic, of course, only for me. Magnetic field intensity. You later on see that this capital B is denoted, is called by other names as well. It is also called magnetic induction. Okay, B is also called magnetic induction. B is also called magnetic flux density. Okay, so let me write the different names over here. Magnetic induction. It is also called magnetic induction. B is also called magnetic flux density. In the videos to follow, we will see, you know, why we have these names. All right. But for now, let us stick to magnetic field intensity. Let us call it magnetic field intensity. So Biot and Savart's law tells us the magnetic field intensity dB at a point P due to the current carrying elemental length IDL is, okay. Before we proceed, B is the magnetic field intensity at a certain point due to current flowing through the whole wire. All right. So if B is the magnetic field intensity at a point due to current flowing through the whole wire, the magnetic field intensity at point P due to the small current element, okay, will be small here. The magnetic field at P due to the small current element will be small. So that small value of magnetic field intensity is dB. Okay, so I again repeat, mind you, Biot and Savart's law gives you the magnetic field intensity at a certain point due to an elemental length, due to current flowing through an elemental length dl. Okay, So, Biot and Savart tells us the magnetic field intensity at point P, dB, due to this current element IDL, is given by or is directly proportional to the current I flowing through the conductor. So dB is directly proportional to the current I. More is the current flowing through DL, okay, more will be the value of the magnetic field intensity. Okay, directly proportional, remember. You very well know what it means. Directly proportional, what it means, you very well know. Okay. Number 2, directly proportional to the elemental length dl. So dB is directly proportional to dl also. That is, greater the length dl, more will be the magnetic field intensity. Smaller dl, smaller magnetic field intensity. No dl, no magnetic field intensity, of course. Number 3, directly proportional to the sine of the angle theta between the elemental length dl and the line joining dl to the point P. Okay. So the magnetic field intensity at point P dB is directly proportional to sine of this angle theta. So what is this theta? Theta is the angle made by the current element, okay, current element with the line joining the current element to the point P, okay, which is this line. Okay, so this line is the line joining the current element to point P. So therefore theta is the angle between DL and this line. Okay, so that is exactly what we are saying here, where theta is the angle between the elemental length DL and the line joining DL to point P. Okay, and finally number 4, inversely proportional. dB is inversely proportional to the square of the distance r between DL and point P. So dB is proportional to 1 upon r squared, where r is the distance between point P and the current element, mind you. Okay, so magnetic field intensity is inversely proportional to the distance squared. Okay, so greater is r, of course, all right, lesser will be the magnetic field intensity. So combining these 4 points, so dB is proportional to I, dB is proportional to dl, dB proportional to sine theta, dB proportional to 1 upon r squared. So combining these 4 points, what we get is dB is proportional to I dl sine theta by r squared. Okay, now you very well know proportionality sign can obviously be replaced by an equal to sign, provided we add some constant. Okay, and this is what you get then after. So dB is equal to mu naught by 4 pi I dl sine theta by r squared. Like you had epsilon naught when we did Coulomb's law, and epsilon naught was permittivity of free space. Permittivity of free space. Okay, so likewise mu naught is a constant. Okay, mu naught is called permeability of free space. Many a times I have seen students getting confused between epsilon naught and mu naught. Sometimes they call this permeability, they call this permittivity. Okay, so check the names correctly and be very, very sure about it. Epsilon naught is called permittivity of free space, mu naught is called permeability of free space. What was permittivity? Permittivity was the measure of how many electric field lines are being allowed to pass through a certain medium. Okay, that was the measure of permittivity of that particular medium. Permeability likewise is a measure of how many magnetic field lines are allowed to pass through a given medium. Okay, so remember that. This is about how many magnetic field lines are being allowed to pass through. This is about how many electric field lines are allowed to pass through. Remember that. The value of mu naught is 4 pi into 10 to the power minus 7 Newton per ampere squared, or 4 pi into 10 to the minus 7, same value, Weber per ampere meter. WB, capital W, small b. This is called a Weber. Okay, Weber is the unit of magnetic flux. Alright, so therefore remember Newton per ampere squared and Weber per ampere meter, they are one and the same thing actually. Alright, like saying kilogram meter per second squared and Newton. Okay, or kilogram meter squared per second squared and joule. It's something like that. You can see these two units are, you can check yourself, these two units are one and the same thing. And by the way, let me tell you, Weber is another name for volt into second. Volt multiplied by second is what is called a Weber. And Weber happens to be the unit of magnetic flux. Okay, remember electric flux? Electric flux, you dealt with this in Gauss's theorem. Okay, electric flux was E dot ds. So like electric flux, okay, you have magnetic flux denoted by a phi subscript m, which is equal to B dot ds. So this is electric flux, and the unit of electric flux is what is called a Weber. Okay, so don't forget this value of permeability of free space. Okay, so this is the expression that you get from Biot and Savart's law. Remember, dB is mu naught by 4 pi I dl sine theta by r squared. And by the way, the unit of B, magnetic field intensity, is Tesla. This is the SI unit, and the other unit is Gauss. Okay, 1 Tesla is 10 to the power 4 Gauss. This is the relation between Tesla and Gauss. Just to give you an idea about how large these units are. Okay, the value of magnetic field intensity of the Earth. Okay, remember Earth also is a huge magnet. Okay, magnetic field intensity of the Earth is about half a Gauss. So Tesla is a big unit, remember. The unit of magnetic field intensity of the Earth is about half a Gauss. Okay. Now we are going to look at two very, very important applications of Biot and Savart's law, remember. Now I'm saying important with respect to your taking into consideration your examination. Okay, these two applications of Biot and Savart's law are very, very important, taking into your exam into consideration, Okay, so we are going to look at these two applications. So each application will take one video, I think. All right, will take about 10-12 minutes. So we'll make one video for each of the applications. Very, very important, I'm telling you. Okay, furthermore, let me show you one simple thing. Okay, that is vector form of Biot and Savart's law. Sometimes you get a 1-mark question stating that write the vector form of Biot and Savart's law. So this is the expression for Biot and Savart's law that we got: mu naught by 4 pi I dl sine theta by r squared. This needs to be by heart, remember. Okay. Now, so dB can also be written as multiplying and dividing by r. So I dl r sine theta by r cube. Okay. So this thing can be written as I dl cross r divided by r cube, of course. So this is the vector form of your Biot and Savart's law, remember. Okay, so with this, let me stop this video. Okay, so give a nice look at this Biot and Savart's law, remember. I've only introduced you to Biot and Savart's law in this video, and I'm telling you it's very, very important. Okay, Biot and Savart's law, and these applications I was talking about, these two applications, okay, each will carry about 5 marks in the exam. Okay, at the very least it will carry 3 marks. Okay, but sometimes I have seen this carrying 5 marks. These are lengthy derivations that we need to do. All right. Okay, so anything you don't understand, do let me know, class 12. I've been repeatedly telling this. So far none of you have asked me any questions. Okay, so many videos I've made. Any problem you have, do let me know. Take care.